All right, so let's talk about electrical power. Now, power is work divided by time, or change in potential energy divided by time. So let's actually put this in terms of potential energy now up here. Power equals delta U over time. And now from our last unit, static electricity, I know an equation that has delta U. Delta V, right, or electrical potential difference. In this unit, we're just using V, voltage, instead of delta V for it, or change in electrical potential, because that's what's happening here in this unit. That's going to be delta U divided by Q, meaning that delta U must equal delta V Q. So I'm going to substitute that in now into this equation. So power must equal delta V Q divided by T. And now notice something here. That delta, instead of changing our electrical potential, it could be the amount of charge that is changing as well. And check out this idea. Q divided by T. Well, I know what Q divided by T is from our equation. I is going to be delta Q, change in charge, divided by change in time. Q divided by T is I, which then leads me to P equals VI, right? Or the base equation for electrical power. Power equals current times electrical potential difference, aka voltage there. Then, very simply, and I'm not actually going to show this proof, showed the proof to get to that base equation, but I'm not going to show the proofs for these. You use the idea of Ohm's law, right? V equals IR. And you solve around for, let's say, here we have it solved around for V already. So then you can take that and substitute IR in for V and come out with power equals I squared R. Or you can solve around for I, right? Substitute that in over here and come out with power equals the voltage squared divided by R. So here are your other two good equations in terms of resistance if you need. But like I said, this is the main equation. From also this idea of power, we can get electrical energy that is expended, or the energy, remember, is going to be power and involves power and time. So coming back to our power equation, power equals change in energy. I'll use delta E. Really, it's delta U, but we'll use change in energy right now, divided by time. And we now know that electrical power is IV, is delta E, or the amount of energy expended divided by time. I think you can see where this is going. If you multiply the T to the other side, you get current times voltage times the amount of time that you allow it to run is your change in energy. Thus, our base electrical energy equation, the amount of energy expended, the amount of electrical energy expended is the current flowing through an object times the electrical potential difference you are having, or the voltage you are having to exert, times how long you let this thing run, whether it's an electric motor or anything else. Now, here in the United States and really across the world, you hear electrical energy. Remember, energy has base units of joules, right? But you'll hear energy talked about in terms of kilowatt hours, or the amount of energy used by a device that's using up 1 kilowatt of power, and you'll let it run for an entire hour. So you'll hear things in terms of kilowatt hours, but that's not our base unit. Our base unit is joules. So how do you convert back and forth, back and forth? Well, that's actually very, very simple, looking just at the power equation. So power is delta E, or energy or work, divided by time, right? And we're using 1 kilowatt. Let me multiply the time on over to get it in terms of delta E, power times time. We're using 1 kilowatt, which we know what that is. That's 1 times kilo to the third. We're using 1 kilowatt. So that gets 1 times 10 to the third, gets us back into watts, base unit. And time for 1 hour. Well, we know how many seconds are in an hour. 3,600. 60 times 60, right, equals delta E. Back in our base units of base unit of watt, base unit of seconds, whenever you multiply those together, delta E in joules, so you stick those in your calculator, and really you don't even have to stick that in your calculator, it's just 3,600 times 1,000. You come out with 1 kilowatt hour is equal to 3,600,000 joules worth of energy. Now that we know the equation for electrical power, base equation power equals IV, let me take you back to a problem from thermal energy that we did, a common one, an electric water heater, right? We were solving for flow rate, or maybe they give us the flow rate and we're determining how much power. Now instead we could use how much current or how much voltage must be applied. But here's a problem, right, where I'm going to use my idea of power equals delta E over time, or work divided by time. It's just what's going in now is electrical power, so I can set up my left-hand side to be IV, and the energy, where this energy is going, is delta Q to heat water divided by time. And so now I can get IV equals MC delta T divided by time. And then, of course, your M over T, and I'm going to have trouble drawing this, but your M over T becomes your flow rate. So you end up with IV equals M divided by T C delta T, right? So it's the exact same thing as what we did back in the thermodynamics unit, except now my power actually can become, excuse me for erasing that, IV right here. But I'm not going to go actually solve that problem. I want to come down here and solve another problem that is very, very similar. Now, sewage lines. Not many people like to talk about it, not many people like to think about it, but let's be honest, it's kind of necessary for our society. We need something to take the waste away, because the last thing we want to do is keep it around in the house with us, and that's where sewage lines come in. Now, sewage lines actually operate based upon gravity. The sewage flows downhill. And so they try to design an entire septic or sewage system to where all that has to happen is gravity pulls it down to the wastewater treatment plant. And, you know, if you have to push it up a hill, which occasionally does happen, then you have to exert energy to get it over. And so in some places, they try to design to have minimal number of these, but in some places you have no choice. You have to take your sewage and pump it up over a hill. Like in our problem, we're going to pump the sewage up over a 35-meter ridge to where it can then continue to go down towards the wastewater treatment plant. And the pump that I'm going to use here draws 2.5 amps from a 120-volt power source. My question here first is how much sewage can be lifted over the ridge line per second? That would be a flow rate, if you catch that. And then the second question is going to be how much it costs based upon that amount of money per kilowatt hour. So let's start out looking for a flow rate. How much sewage per second? Power equals delta E, or work, right? Delta E or delta U over time there. In fact, let's come back in here and let's make this delta U. That would be more correct there. Change in work or change in potential energy divided by time. And the power that I'm exerting is electrical power, IV. And the type of energy, so I have electrical power going in, and the type of energy coming out is gravitational potential. I'm trying to lift the sewage up some hill, mgh all over T. And I can combine my mass divided by time into a flow rate again, so IV equals m over T gh, and that allows me now to plug chug. And whenever I solve that through, I come out with a flow rate mass divided by time of 0.87 with my 2 sig figs allowed up here. 0.87 kilograms per second is how much waste can be pumped up this hill effectively by this pump. Now let's deal with the second part of this equation. How much is it going to cost the wastewater treatment plant or company to operate this pump at this location for an entire month at the power rate of about 9 cents per kilowatt hour. Now, a kilowatt hour is a unit of energy. It's not our base unit of joules, but it's still a unit of energy. Meaning, first thing we need to do is solve for how much energy this thing is going to use. Now, we know the equation for energy. We derived it on the last slide there, and energy is IVT. Here, and so the amount of energy that we are going to expend here is going to be my 2.5 amps. Notice this is in amps base unit, not milliamps, and 120 volts instead of millivolts or anything else that would require scientific notation, times time, and that's going to be the number of seconds in a month. So we'll take 1 month to be approximately 30 days long. You know, it could be 31, it could be 28, but approximately 30 days long on average, 24 hours in a day, 60 minutes in an hour, and 60 seconds into a minute. And I come out with 777,600,000 joules of energy. But that's not in kilowatts yet. I need to divide that number by the amount of energy 1 joule has per kilowatt, 3,600,000. So to get into kilowatt hours, I divide by 3,600,000. And I come out with a kilowatt hours of 216 kilowatt hours, and then I come back up, I look at my problem, it says that 9 cents per kilowatt hour, so now I'm going to multiply by 9 cents. And I come out with a cost of $19.44. If I'm using sig figs here, we're going to treat the cost of 9 cents to be exact, since you can't have half a cent in there, no half pennies. So with 2 sig figs, it would be $19 would be the correct answer there. On the other hand, if you're running a business, it would be much wiser to choose to round up, just in case. You want to build margin in your business. $20 would be a much wiser idea of how much that pump is going to cost you over the course of that month.